next we have Raffaele Santagati, who's going to be talking about quantum information processing at SQP.
Silicon quantum photonics. Good afternoon, and thanks a lot for giving me this opportunity to present this talk. And I'm Raffaele Santagati. I'm a postdoctoral research associate here in Bristol. And the work I'm going to present is the results of a couple of years of experiments we've been doing here in Bristol, and how to bring quantum information processing performed in silicon quantum photonics. So I want to thank also all these people here that actually contributed actively and was part of a really big team that allowed us to do these experimental demonstrations. And in particular, these guys here that are like a bit the quantum simulation team here in Bristol, and with also Sebastian, that is our NV man. And here instead we are having dinner with one of our collaborators, that is Nathan Wiebe from Microsoft. I don't know how much is visible from there, but we were having some very nice Chinese food. And also like Gerald McLean and David Chiu that worked a lot on giving us theoretical support. So I'm going to talk about briefly about silicon quantum photonics and why we think it's a good technology and why it's suitable for some quantum information processing. And then I'm going to introduce these three experimental demonstrations that are, namely, first, they are all based in connected to quantum simulation. And the first one is on, like we are showing a new method to find the excited states or Hamiltonian, and using variational methods. And the second one will be an experiment that's called Bayesian phase estimation, where we use Bayesian inference to make the phase estimation algorithm more resilient to noise. And the last experiment is about Hamiltonian learning, where we basically use the machine learning and quantum simulator to learn efficiently the Hamiltonian parameters of a physical system in an experiment where we use a silicon photonic quantum device to learn the Hamiltonian of an MV center. So why we like silicon quantum photonics or silicon photonics? Because as Dylan said yesterday, it has a very high refractive index contrast, and so the components can be made very small. They can be ultra compact. The waveguides are of the order of 450 nanometers by 220 of height. And these, let's say that with silicon photonics, we inherited all the manufacturing process that was developed for electronics. So it's quite advanced and it's quite reliable. And the high nonlinearity allows us to, gives also problems, but in particular allow us to have like integrated photon pair sources in chip. And it's been demonstrated that you can integrate also detectors, filters, and we are integrating also the manipulation, the component necessary for qubit manipulation. So I will not spend too much time on this. Everybody knows basically what the two-rail encoding is. We have the path encoded qubit. A photon is in one waveguide, is at 0. If it's in the other waveguide, it's 1. And then we can manipulate the state of the photons using directional couplers or phase shifters. In this particular case of silicon, the phase shifters are realized with the thermo-optic phase shifter with the heaters. One interesting result was 2013, where it has been shown here in Bristol that we can obtain high visibility quantum interference using multiple of these sources. So using two different sources, we can observe this high visibility quantum interference. And right after, a couple of years after, we demonstrated also that we can integrate different components, increasing the functionality of these. So sources, filters, and qubit manipulation. Here we are, the device I would like to present now is instead a device that can perform arbitrarily controlled unitary operation. It was fundamental for us to show these applications in quantum simulation that we demonstrated. So this device, how it works, it has like these two sources here that are generating an entangled state. At this point, we have like a bell state where the photons can be here, or so in the first waveguide or the third one, or in the second one and the fourth and the last one. So it's a state that is 0, 0, 1, 1. If we just perform tomography on the control, so we don't do nothing on the control, but in the target, we prepare the state, and then we use the fact that in linear optics we can just increase the number of modes, and have like one component, the component that corresponds to the 0 of this qubit, going through an identity operation, while the component that corresponds to a 1, it goes through the unitary we want to implement. Now, if we erase the path information, whether the photon went through the identity or the unitary, we can obtain at the end the same output statistics you would have obtained with a controlled unitary operation. So why we wanted to have this controlled unitary operation? Because it's like the fundamental ingredient to be able to implement the phase estimation algorithm. That is like one of the most famous algorithms for quantum simulation. And we wanted also to implement a new method that we thought for realizing to solve the eigenvalue problems. And in particular, we wanted to solve the Hamiltonian spectra of exciton transfer in chlorophyll. So the method we use, we call it waves. It means witness-assisted variational eigenvalue solver. Why we call it witness-assisted? Because we introduced a concept that is called Eigenstate Witness, and that is telling us if the state we are testing is an eigenstate of a given unitary, of a given Hamiltonian, or not. If this eigenstate witness has a particular value, then the state is an eigenstate, otherwise it's not. And we use this eigenstate witness to perform the variational search. So first of all, we search for the ground state, that is the global minimum of the energy, while the excited states are the local minimum of the energy, so are more difficult to find. And after we apply some excitation guess operators, like shown here, so we first find the ground state, then we apply these guessed excitation operator that bring us close to the excited state, and then we refine our guessed state by variationally optimizing our eigenstate witness. And we perform this for each of the eigenstates, and at the end of the variational search, we perform the phase estimation algorithm that has the particular property also to project the state further into the closest eigenstate. So how it works, just to say quickly what is this eigenstate witness, it's basically an entanglement witness. So what happens here is we prepare in the target qubit, in the target register, we prepare variationally using an ansatz that is describing our system with a polynomial number of parameters. We prepare the state that needs to be tested, and then we evolve it through a controlled unitary, which is implementing the unitary is the unitary relative to the Hamiltonian. And at the end, we perform tomography only on the control qubit. At this point, if the state in the target register is an eigenstate of the unitary, the state emerging from the controlled unitary will be separable. So the purity of the control qubit will be 1. And we know that the state we input in the target register is an eigenstate. If instead the target register has not an eigenstate in it, so it's a state that is not an eigenstate of the Hamiltonian and then also of the unitary, what will happen is that the state emerging from the controlled unitary will be slightly entangled or completely entangled, depends on which state it is. But when we perform tomography on the controlled register, the purity will be lower than the 1. Then this is how this method works. Once we find the ground state, then we apply these guessed excitations operators that are given by our knowledge of the chemistry or the physics of the system. And these are the experimental results. In this case, we found both the ground state and the excited state. So you can see that the objective function goes rapidly to its minimum, and the fidelity, this is the fidelity with the target eigenstate. It goes very quickly to the maximal value. So we obtained basically fidelities that were of the order of 1 within the error. And then we performed the iterative phase estimation algorithm with 32 bits precision. Now, we wanted to know if the method was just working in this particular case, I mean, clearly we cannot test it on a foolproof quantum computer, and we don't have too many qubits. So we wanted to test it in bigger Hamiltonian and see if the method was still working. And we performed the numerical simulations of Hamiltonian up to 8 qubits. And we saw that for all of them, we obtained always the final fidelity of the variational search to be very close to 1. And in all of these cases, the interesting point for us was that within error, increasing the dimensionality of the problem we are studying, the final fidelity will not decrease. And also we also did some other tests where we actually started cutting the legs to our ansatz, making it more difficult for the ansatz to find the target eigenstate. But also in those cases, the algorithm was still finding it. And another thing we wanted to test was, let's try to see what is the effect of noise on our phase estimation algorithm. So the phase estimation algorithm works by estimating the binary fraction expansion of the eigenphase that we want to estimate. And it starts from the least significant digit up to the most significant one. So it works pretty well, and it's one of the most powerful quantum algorithms out there, probably. But it has been shown that in some cases it can have some sensitivity to noise. In particular, there was this result from John Martini's group, where you can see that variational methods finds the ground state with a much higher precision than what the iterative phase estimation algorithm can do in presence of noise. So we said, okay, there must be some method that we can use to try to mitigate the problem of noise. And we met this guy. This guy is Nathan Wiebe from Microsoft, which last year with Chris Grenade and Chris Ferry demonstrated, did a proposal, a theoretical proposal. It was published last year, but the theoretical proposal was of 3 years ago. He proposed to use Bayesian phase estimation, so to use Bayesian inference to perform the phase estimation and transform it from an iterative algorithm to an inference problem. So at each iteration, the problem will be inferring what the eigenphase we are trying to estimate is. And how it works. So we encode, we store the information of the eigenphase into a prior probability distribution. And then we perform a measurement on our quantum device with the m and theta, the correction and the order of the unitary that are chosen by the algorithm itself. And depending on the outcome of the measurement, then we update this prior distribution we had with the bias rule. And we can see how the algorithm starts with a very broad distribution of the eigenphase and then ends up like converging around the correct value. And this is actually, like, just to show a video that Stefano prepared, where we see the algorithm converging to the correct eigenphase in just this is 50 iterations, and we got like a very small error. And then we compared the noise resilience to the noise resilience of the phase estimation algorithm. So now we started like getting our quantum photonic chip with some error in it. So we started setting the phase instead of to the value we want. We started sampling the values from a Gaussian distribution with a sigma in the Gaussian that was increasing. So we were increasing basically the noise in our phase shifters. And doing that, we see that while the standard iterative phase estimation algorithm with an error of just 0.03 radians on the phases, it becomes quite unreliable. The rejection filtering phase estimation, I don't know still if you can see very well because of the light, but the rejection filtering phase estimation, the Bayesian phase estimation, it can still obtain the right eigenphase with an error of the order of 10 to the minus 2 radians, also when the error on the phase shift is of the order of 0.5 radians. So it looks like it's much more reliable in a non-error corrected machine than the standard phase estimation is. And the last experiment I wanted to talk to you about is Hamiltonian leveling. So in this case, what we wanted to demonstrate is trying to use machine learning, so Bayesian inference and quantum simulation to learn efficiently the parameters of a physical system. So this is based on the idea that a quantum simulator can actually efficiently simulate the dynamics of the physical system. So if we have something that can simulate dynamically the dynamics of the system, and on the other side, we have a machine learning algorithm that can control both the experiment and the quantum simulator, we show that we can efficiently learn the Hamiltonian of the physical system under test. So again, we are using a Bayesian method. In our case, we were using a photonic quantum simulator to learn the Hamiltonian of an MV system. In particular, what we wanted to learn was the frequency of the Rabi oscillations of this MV system. The algorithm is called the QLE, quantum likelihood estimation, and what it does is a bit similar to what the Bayesian phase estimation does in a way. Because what does it do is it chooses an experiment, for example, choosing the evolution time t, and based on the prior distribution we have on the parameter space of this Hamiltonian, and then obtains the data from the system and use the quantum simulator to calculate the likelihood of each of the possible values in the parameter space, the likelihood that each of the possible values in the parameter space can have compared to the measurement just done. And then use, again, Bayes' rule to update the prior distribution we had before. And in this particular case, we were observing this MV system. This experimental setup was Seb, and this one was Chang Wei, Stefano, mine, and Andreas, that we were controlling the silicon quantum photonic chip. And what we observed is that in this case, our uncertainty on the Rabi frequency, it decreased continuously with the number of measurements. And in particular, what we can see is that with just a few, like after 30 iterations, it almost converged to a value that is with a very small error, and is very close to is basically around the correct value, as you can see here. And at this point, we asked another question. We were looking at this image, and we were seeing, look, it's learning. This is the sigma squared. And we were seeing that the sigma squared was decreasing. The fact that the sigma squared on the distribution is decreasing means we are learning physics from the experiments we are doing. But at some point, this learning stops. So the sigma squared is saturated. At this point, there could be two problems. Problem one could be our quantum simulator is not good enough and cannot replicate correctly the physics of the physical system, or the model that we are considering is not good enough. And in our case, was the model. Because what we did was we considered another model where we added some, this was the model we were using here, and then we added some time dependence on this model. And what we observed is that when we did that, the Hamiltonian learning algorithm was able to still increase the knowledge and decrease even more the sigma squared. And here you can see like there is a small comparison of the model 1 with model 2. In conclusion, like I hope I gave a very brief overview on silicon quantum photonics and why it's interesting for doing quantum information processing. And I think that the three experimental demonstrations are really showing that with this technology you can start doing something we think useful, something not just fun but also useful. Like waves, I think we can show that it has the ability to target excited states that so far has been done only theoretically, not experimentally. And why the Bayesian phase estimation seems to have to be much more reliable to experimental noise. And the Hamiltonian learning, we think that is a new exciting application for quantum simulation that we are sure will find further application in the future. Thanks a lot for listening.
Thank you, Raf. So, we've got questions. I'll just go this way.
So, maybe this is too technical of a question, but maybe require further discussion later. But one of the important inputs to doing Bayesian analysis is the prior, your initial prior. And other than you picked an initial prior, did you? It's unclear to me how you. I mean, naively, I would have chosen a uniform prior.
Yes.
But then a uniform prior, you had to decide
It's
over
very
what space.
unefficient.
Yeah. So what did you do for your prior, your initial prior?
So in this case, like for example, we started with a prior. In the case of the Hamiltonian learning, was very close to a constant prior because it was very broad. So the sigma was sorry, I lost it. The sigma started with was very broad, and it was very in the 2 pi was very big. In principle, we can use for the parameters in the Hamiltonian learning, we can use our knowledge that we already have on the physical system to start with a reasonable prior, and then if that doesn't work, like we can change our prior and try again. But the nice thing I think is that Bayesian also tell us, well, like on what if we are actually learning something, or if the model is just not learning nothing from the experiments. That I think it's a very nice and exciting characteristic.
Okay.
Yeah, my question is about the Eigenstate Witness. So in that case, how do you measure the separability of the output state? That tells you whether it was an eigenstate or not.
Yes, what we do is we perform single qubit tomography on the control register only, and we trace over the target register. So if we look at the purity, sorry, it's very far. Just a moment, I'll take the slide. Yeah. So if we look at the purity, oops. If we look at the purity of the state only in the control qubit, tracing over the target register, this can give us an estimation of the separability of the state. And we basically use the linear entropy in this. In general, it would be better used than the von Neumann entropy, but the linear entropy is a first order approximation of the von Neumann entropy. So that's good. Thank you.
Okay, any more questions for Raf? Okay, if not, then we'll carry on. So let's thank Raf again.